Two friends A and B are playing a game with a die. A starts the game by throwing the die. If there appears 6 on it, A wins the game and game ends. If 6 doesn't appear in first throw, then it is turn of B to throw the die. If 6 appears, B wins, otherwise again it is turn of A to throw the die. Game continues in this way and first person to get the 6 wins the game. Find the probability of winning of B. You are watching Brain Exploders, the world where brain starts working. Before solving the problem, let us get familiar with some of the terms which we will use in this problem. First one is mutually exclusive events. If there are a number of events in which no two can ever occur simultaneously, then together they are called mutually exclusive events. Other one is exhaustive events. If there are a number of events in which at least one occurs definitely on trial, then together they are called exhaustive events. These two events are not opposite of each other, actually they are different. Examples of mutually exclusive events are sunrise and sunset because they can never occur together. A switch may be either on or off. If A, B and C are the events of appearing 6, 1 and 4 on a die, then it can never happen together. No of these two can ever occur together. Either it appears 6 or 1 or 4 or none of these. Example of exhaustive events is selecting black pieces of chess and selecting white pieces of chess. If we select a piece of chess, it will be either black or white. Another example is selecting black pieces of chess, selecting white pieces of chess and selecting pawns. Selecting pawns is added in the first example to make it the second example, just to show that exhaustive events need not be mutually exclusive too. Here, sunrise and sunset are only mutually exclusive events. They are not mutually exhaustive because sometimes there is neither sunrise nor sunset. For example, afternoon or evening, etc. But switch on and switch off are mutually exclusive and exhaustive events because either the switch will be in on position or off position. None of other situation is possible and one of them will certainly occur, and they cannot occur simultaneously. On throwing a die, 6, 1 and 4 cannot occur together, so they are mutually exclusive events, but it is not necessary that one of them definitely occur, so they are only mutually exclusive, not exhaustive. From 64 pieces of chess, selecting black pieces and selecting white pieces of chess are mutually exclusive and exhaustive events because these two will not occur together and one of them will definitely occur. In the fifth example, selecting pawns is the additional condition which make these events mutually exhaustive but not exclusive because a black pawn may be selected and a white pawn may also be selected. If E1, E2, E3 etc. are mutually exclusive events, then probability of occurrence of E1 or E2 or E3 is equal to probability of occurrence of E1 plus probability of E2 plus probability of E3 and so on. And since these are mutually exclusive events, so they cannot occur together, so the probability of occurrence of any two of these events together is also 0. In case of exhaustive events E1, E2, E3 and E4, probability of occurrence of E1 or E2 or E3 or E4 is 1 because at least one of these will certainly occur. One more term here is mutually independent events. If occurrence of some events are completely independent of each other, then they are called mutually independent events. For example, from two different decks of 52 cards, selecting a random card from each deck are mutually independent events because selecting a card from one deck does not affect the selection of card from another. Appearance of numbers on throwing two dice simultaneously are mutually independent events because number on first die does not affect the number on second die. Similarly, if a die is thrown twice, then also number on the first throw does not affect the number on the second throw. For mutually independent events even E2, E3, probability of occurrence together is P E1 times P E2 times P E3 and so on. In the game described in the question, winning of A and winning of B are mutually exclusive and exhaustive events. So, probability that A wins plus probability that B wins is equal to 1 and probability that A and B wins is equal to 0. There are infinitely many cases in which game may end. In the first case, there is that A throws the die and wins by getting a 6. In another case, A may throw the die and does not get 6, then B throw the die and get 6. Game ends and B wins. In the third case, in first throw, A may not get 6. In the second throw, B may not get 6. And in the third throw, A may get 6 and win the game. In this way, infinitely many of the possibilities are here in which game may end. Number going to be appear in any throw is independent of the previous throw, but all the infinite cases are mutually exclusive and exhaustive, because if game ends like case 1, then obviously it may not end like case 4, and if it ends like case 4, then it may not end like case 3 and so on. So any two cases here cannot appear together. Now first we will solve the problem for 6-sided die, then for n-sided die. For 6-sided die, let E6 is the event of getting 6 on the die and E6 prime is not getting 6 on the die. We know that probability of getting 6 is equal to 1 by 6 and probability of not getting 6 is equal to 5 by 6. Now in the first case, A has to get a 6, so probability of case 1 is 1 by 6. In the case 2, A should not get 6 and B should get 6. So probability of not getting a 6 is 5 by 6 and probability of getting a 6 is 1 by 6. These are completely independent. So the probability of case 2 is product of these two. Similarly, in case 3, there are two throws in which we are not getting 6 and one throw in which we are getting 6. These are completely independent. So the probability of case 3 is product of the probabilities of all these three, which is 5 by 6 whole square times 1 by 6, and in this way probability of all the cases can be calculated. If A has to win, the game must end like case 1 or case 3 or case 4 or case 7 and so on. All these cases are mutually exclusive, so probability that A wins is probability of case A1 plus probability of case A3 plus probability of case A5 and so on. On putting the values and on further calculation, we find that probability that A wins is 6 by 11 and probability that B wins is 5 by 11. For a n-sided die, we just have to put the probability of getting 6 equal to 1 upon n and probability of not getting 6 equals to n minus 1 upon n, and in this way we get that probability that A wins is n over 2n minus 1 and probability that B wins is n minus 1 over 2n minus 1. This was our solution. Let's move to our another question. There are 10 boxes which contain 10 balls each. All the balls look identical, but the balls of exactly 9 boxes are of equal weights. Balls in 10th box are 10% lighter than the balls of other boxes. You have an electronic weighing machine which tells the exact weight of the object. What will be your strategy to identify the lighter box in minimum number of weighings? Try this question and send us your solution, and if you have any question like this, then please share with us. Don't forget to like and share our video, and for more such videos, subscribe to our channel Brain Exploders. Thanks for watching.